Okay. So this is the ninth lecture. Obviously, it's delayed somewhat due to the anomalous low temperatures that happened in Austin. Uh, but what I've decided to do is just to try to compress the lectures a little bit in order to get back to the place we wanted to be. Okay. So, what we can talk about in this lecture is the first real connection between what we're doing in this course and what's commonly known as statistics. So, the way I usually construct the definitions of these words is that probability is a formalism in theoretical mathematics, which consists of the three axioms we discussed in the beginning of the course, together with all of the logical and arithmetic consequences of those axioms. So, on the other hand, I think of statistics as a part of human society that tries to use this abstract mathematics to give useful conceptual meaning to numerical data. So, as a scientist, what you're always trying to do is to understand the observations you're given. And in 2021, what that means is any kind of serious STEM project involves absolutely gigantic amounts of numerical data, billions or trillions, if not more, bits. And, there's just no way for the human brain to inspect so much data, let alone come to any sort of predictive or technological conclusions from it. So, what we have to do is to use the math we're learning in this course to do what math does and manipulate information in order to reveal important aspects of it which are not transparent without the relevant mathematical insight and procedure. So, what we're going to do in this lecture is talk for the first time about a mathematical procedure which really conforms closely with this paradigm of probability as a tool to attach conceptual meaning to large amounts of numerical data. So, if you talk to somebody who has no idea that higher math exists, like I think at least 90% of people in the world just don't understand that mathematics is something that happens for its own reason rather than just because authorities have told them that it happens. And, you can't blame people for that because they simply haven't been exposed to the idea that math does not derive its authority from people. But, even if you don't know that it's possible to think about math rigorously, you know that there's all this numerical information thrown around in the media and by politicians and even by medical personnel that uses the word average. And what people understand by that is that if someone tells you the average value, they're telling you a reasonable expectation for something about which they are uncertain. So it's like, if I say, oh, on average, I wake up once a day, that's pretty clear what it means. It means that sometimes I've woken up more than once a day, and sometimes I've woken up less than once a day, but in general, I wake up once a day. And the idea of averaging that's actually not a good example because most people haven't woken up less than once a day very often. I have done that in my life for atypical reasons, but anyways, let me try to think of a better example. So a better example would be if I say that, like, on average it rains once a week here or something. So on average it rains once a week, oh, well, sometimes it rains more than once a week, sometimes it rains less than once a week, but I should walk around roughly expecting that it's going to rain once a week. So if you think about science as a way to help people understand the world, what the idea of an average does is it tells someone what they're supposed to expect as a kind of baseline for something that varies or changes in a way that's unpredictable. And so, what this ends up meaning is that the concept of an average is universally understood as the best way to summarize a numerical data set with a single number. So we will introduce the probabilistic concept of expectation, which generalizes the idea of averaging. And I think the word expectation is an excellent choice here for whoever decided that, because the expectation of a random variable is what you should expect it to come out to be. Random variable is the noun, and to which we're going to attach the prefix expectation. So we're going to talk about expectations of random variables. Okay, so we can interpret an average as related to a uniform, discrete random variable where we add up the values of the measurement function at each point in the sample space. Let me change the word point to be more consistent here. I'll change this word to outcome. Okay, so I have a very abstract sample space here where I've just said that, okay, the elements of my sample space are the natural numbers between 1 and n. And so this is just what any reasonable mathematician would take as an elementary example of a set with n elements. A computer scientist might want to consider the set of integers between 0 and n minus 1, which is also a pretty reasonable thing to do. But this is just supposed to represent a abstract sample space that can correspond to any sample space with n elements if you just enumerate the elements of the sample space in some arbitrary way. And then you can see on the right of the middle of the page, I've written out there what hopefully you'll recognize as the familiar definition of an average, except I've tried to connect the notation with what we've been using for measurement functions, where we're thinking of the measurement function as assigning a real number to every element of the sample space. So, what we want to do with the idea of expectation is just generalize this concept from adding up all of these random variables weighted by 1 over n to thinking of 1 over n as corresponding to the size of a single outcome event in a uniform probability space, and instead of adding up the values of the measurement function all given the same weight 1 over n, we want to weight the values of the measurement function by the probability they occur. So weighting the values of the measurement function in the sum by the probability, or weighting the values of the measurement function in the sum by the probability that the underlying outcome occurs is what the generalization of an average means conceptually. So you have a uniform probability space where every outcome has weight 1 over n. And expectation in a uniform probability space corresponds to the notion of an average, which is understood by people with no mathematical training. And then what we want to do with the mathematical concept of expectation is to say, well, there's nothing specific about the uniform probability space that makes this work. Instead, we can just weight each value of the random variable by whatever the appropriate probability is for the underlying single outcome event. So this is a sense in which expectations are weighted averages. Expectation is such a profound concept that it has several different reflections in different fields of mathematics and science, and because of that it goes by different names. Like, the most explicitly descriptive name would be weighted average. To a person who's doing mathematical analysis or is familiar with the traditions of classical math, you might call an expectation a mean. So you would say that the elementary concept of an average is the arithmetic mean, and we have various other methods of constructing means. And obviously, as I'm trying to suggest, in probability and statistics, the concept is called expectation because it's supposed to tell you that the expectation of a random variable is the most reasonable guess for what it should come out to be. So in terms of actually calculating expectation, the way you always do it is you say that explicitly working with measurement functions and sample spaces is always going to overwhelm you with data, and whenever possible we need to use higher level concepts in order to avoid falling down a black hole of complexity such that the human brain no longer has the volume of information capacity to understand what's going on. So in order to actually work with expectations using your own brain, what you need to remember is the formula highlighted in teal. So I won't go through the details of how to derive the formula highlighted in teal from the concept of weighted averages, but it's basically just collecting like terms where the value of the random variable is the same. And what this gives you is a sum over all possible values of the random variable of the value times the probability mass function for that value. So in order to calculate expectations, so in order to calculate expectations, what you do is figure out all the values of x, calculate the probability mass function, and then do this sum where you add up all the values times the corresponding outputs of the probability mass function. Okay. So we can do an example where we let x be a random variable we were discussing before, which is the sum of the rolls of 2 fair dice. And so the question asks us to compute the expectation of x. So we're going to apply epistemological best practices and say that we calculated the probability mass function of this before in example 8.1. And in example 8.1, we already did the necessary information processing to go from a measurement function to a probability mass function. And because we already processed that information once, we're not going to process it again. We're just going to copy the result from where we stored it, which is in the PDF for example 8.1, which you can access with the rest of the course notes. So what I literally did is I copied that from my own file of example 8.1, and you can see what it comes out to be here. Okay, and so now we have this table with the values of the function and the values of the corresponding values of the probability mass function. And so what we can do is we can apply the required formula. We have these 10 values. Whoa. Hold on a second here. I think I just told a lie, didn't I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have these 11 values, and we need to add them all up, weighted by the corresponding probability mass functions. So you can see the first entry in the sum, the value is 2, the probability mass function is 1 over 36, and so we have the first entry in the sum is 2 times 1 over 36. And hopefully it's obvious how I've just copied the information from the table in the middle of the page into the sum, and computer told me this sum is 1. Well, I'm going to tell you, I'll be very honest, I didn't actually type this sum into a computer. I just knew from previous experience that the sum of the rolls of 2 dice is a standard thing in probability theory, and the answer is 7. So, okay. Anyways, if you want to check, you can type this sum into a computer, and it will tell you that it is 7. So we can see, in terms of working with expectations and trying to get useful results with them, there's an absolutely crucial property that you end up exploiting over and over and over again whenever you're working with expectations. This is just like the absolute first thing you always want to do with expectations, is see whether you can get an advantage by using the properties which are described on this page. So these properties correspond to what a theoretical mathematician would call linearity of expectation as a functional on random variables. So if you've taken a course in linear algebra, expectation is a linear transformation from random variables to real numbers. And what you can see here is that I've written out the definition of a linear transformation in the context of probabilistic notation with random variables and expectation. So if you add up 2 random variables, you want to know what's the expectation. Well, you just take the expectation of each one individually and add up those 2 numbers. If you want to know the expectation of adding up n random variables, you just add up the n individual expectations. And the other useful property is that if you have fixed constants, so c is some real number, expectation allows you to take the constant in or out of the parentheses however you feel is most helpful to you. So the expectation of 5x is 5 times the expectation of x, and the expectation of 0.0687x is 0.687 times the expectation of x. Okay, so the equations highlighted in teal at the bottom of the page are the ones you want to stick in your memory, because those equations combine and summarize both properties, and you can derive the individual properties pretty easily by taking the constants equal to 1 or setting y equal to 0. And so if you remember the equation highlighted in teal, the first equation highlighted in teal, you can remember everything about linearity of random variables. You can exchange the expectation function with addition and scalar multiplication of random variables. And there's also the more general version of the same concept for multiple random variables. But usually what I suggest is just focus on making sure you can remember the 2-element version, and then if you want to use the multiple element version and it's not at the top of your head, you know you can look it up in the same place as you found the 2-element version. So let's see an example of how expectation linearity makes it really efficient to work with the concept. So let's say we roll 87 fair dice. We gain $6 for each dot that shows on the upward faces, and we are negotiating what price we will pay to play the game. Where should we set our red line to walk away? So what the question means by a red line to walk away is a price at which the expectation of your result from the game is negative. So you should refuse to pay a price which forces you to expect that you're going to lose money. So how are we going to determine where our red line is? Well, we're going to calculate the expectation of this offer being made to us, where we get $6 for every dot that shows on the upward face of one of these 87 dice. So how are we going to do this? Well, one thing I am not going to do is force you to calculate the probability mass function for the sum of 87 fair dice, let alone force you to actually compute every single value of the measurement function, because the number of possible values of the measurement function for 87 fair dice or the number of outcomes in the sample space for 87 fair dice is 6 to the power of 87, which is, let me think, I mean, that is getting, like, much larger than the galaxy in terms of physical orders of magnitude. So, you know, we're not going to write out the measurement function for 87 fair dice because the number of outcomes is physically larger than the galaxy. So, okay, what are we going to do? Well, we can use linearity of expectation to our advantage. We can say, let's make 87 different random variables, each of which represents the outcome of one of these dice. So instead of trying to think of one unbelievably gigantic sample space with 6 to the power of 87 outcomes, we're going to break things down and say we just need to consider an individual sample space with 6 outcomes, and then we can use mathematical processing to figure out what we want without writing out a sample space bigger than the galaxy. So in example 9.1 that we just did, we figured out that the sum, if 87 were replaced with 2, the answer would be 7. And so you can either do an easier version of the same calculation we did in example 9.1, or you can cheat and say, well, I can do linearity backwards and just say I already figured out the sum of 2 is 7, so the value for 1 has to be 7 over 2. Okay, but anyways, the expectation for each one of these 87 random variables, which shows the number of dots on the individual dice, is 7/2. And we're getting $6 for each of these dots. So we want to figure out the expectation of 6 times x1 plus 6 times x2 plus 6 times x3 all the way up to plus 6 times x87. And linearity of expectation is going to tell us that we can transform the addition and multiplication from inside the expectation to outside the expectation. And after we've done that, we can see that we're going to have 87 copies of 6 times 7/2. And even though my computer is smaller than the galaxy, it can figure out that the answer to this question is 1,827. So the way we want to interpret that, look, I could do that myself if I really wanted to. I don't want to, but I could do that myself. Anyways, figuring out 6 times 87 times 7/2 is 1,827. I mean, I don't really need my computer for that. But anyways, if we pay more than $1,827, then we should expect to lose money from the game. Hence, playing it would be irrational, and we should walk away from this negotiation. On the other hand, if we are offered the chance to play the game for a price of $1,826, we can say, I have a mathematical expectation of gaining $1 from this game. So if I have $1,827 at my disposal, I should maybe consider spending 1,826 of them on this game so I could gain an extra $1. Alright, so the second most important statistic for summarizing a numerical data set is called the variance. So just like expectation, the name of the concept is really useful in suggesting what it's supposed to mean, because the word variance kind of sounds like it's talking about how something varies around a central point. And the idea of the central point, and yet another way that the concept of expectation manifests itself in science, is the idea of center of mass. So I told you that an elementary thinker would call it a weighted average, a theoretical mathematician would call it a mean, a probabilist or a statistician would call it expectation, and a physicist would call it center of mass or center of gravity. So expectation in physics corresponds to center of mass, and that's another, or the reason I brought that up is because the word variance is kind of suggesting the extent to which something varies around its center. So when you ask what's the variance, it's like, okay, you told me the most important thing about this data set. You told me what I should expect as the average result. Now, given that you've set my basic expectations, why don't you tell me this?
why don't you tell me whether you set that expectation because it's in the middle of a large diversity of things with many outliers and the various differences cancel each other out? Or did you tell me to expect this because there really isn't very much difference and everything is really super tightly close around the center? So it's a question of whether the expectation is what it is because big differences in the population are canceling each other out, or whether the expectation is what it is because there's very little difference in the population at all. And so you can see I have these two little visualizations in the just below the bottom of the page where I've adopted the notation mu for expectation. So if you don't need to explicitly work with the underlying variables, so you're in a situation where you're only considering one random variable and you know what it is well enough that you don't feel obliged to specify it everywhere, a standard thing to do is to write the notation mu instead of e of x for the expectation of x. And this, I think, comes from the fact that theoretical mathematicians call this thing a mean, so we use the letter mu because it's Greek for m corresponding to mean. And the ancient Greeks were the people who really started thinking about weighted averages for the first time. At least, and that we have historical record of. So, yeah, I have these two visualizations in the middle of the page, and you can see the expectation mu is what looks like the center of gravity. If you imagine all of these little green dots are weights, hopefully I've drawn the pictures in a way that suggests if this rod with weights were balanced exactly at mu, it would be stable. And the point is that in the left example, we have a high variance where the weights are balancing each other out from all kinds of different points arranged around the rod, and there's even some weights very extreme at the ends that are not even close to the mean at all. And on the other hand, we have a picture on the right where the variance is low and everything is tightly clustered around the mean. And so if you're trying to make a probabilistic prediction, small variance is a good person who is good for your prediction. It's like somebody says, okay, I have all this data, what am I supposed to do with it? They're going to say, okay, I'm going to calculate the expectation. So I calculated the expectation. Now, how useful is the expectation in telling me what's actually happening with the data? And small variance makes the expectation more useful, because if you have a small variance, it means I can walk around pretty much assuming that the data just is the expectation. It's like, if I have a small variance, I can do what I would really like to do and just pretend that all of this data is constant and it's all just the expectation, because doing that is such an easy way of understanding data, and if you can understand data that way, then you should, because it gives you a very, very detailed path to go forward with decision making and further analysis. So small variance is good because it means expectation is a very reliable prediction. On the other hand, big variance is bad in the sense that you need more careful analysis because you can't walk around just expecting that the data literally is the expectation all the time. Sometimes you're going to see outliers which are wildly different from the expectation because you'll sometimes see outliers in the other direction that cancel them out. Okay, so the way to mathematically formalize this concept of variance is to say that I'm going to ask what I should expect for the square of the difference from the average. The reason we don't ask what you should expect for the difference from the average is because the difference from the average could potentially be 0 due to the expectation of the difference from the average is always 0 due to linearity. So expectation of the difference from the average is always 0 due to linearity, and thus the concept of expected difference from the average is mathematically trivial and not useful. I won't get into the details of explaining exactly why that is. I'm just going to ask you to accept that the obvious thing to do, which is to ask what should I expect for the difference from the average, that just doesn't work. It always gives you an answer of 0. So what I'm going to do is I'm going to ask what I can expect for the square of the difference from the average. And this turns out to be the right question to ask. It's very important in theoretical math, and I don't have expertise in other sciences, but I think it's also important in other sciences to have a concept of asking the right question. So the right question to ask is not the obvious one, what's the difference from the average? The right question to ask is, what should I expect for the square of the difference from the average? And again, for mathematical details I won't get into, there's a much easier way to calculate variance than to use the definition and calculate the expected square of the difference from the average. The easy way to calculate variance is to take the expectation of the square and subtract the square of the mean. So expectation of square minus expectation squared, or usually in order to avoid awkwardness with having the same expectation symbol playing two subtly different roles, I like to write it with mu for expectation. So I have the expectation of x squared, and I'm subtracting mu squared. And there's just a piece of notation or a piece of terminology that you need to know. Often people talk about standard deviation instead of variance. Standard deviation is the square root of variance. You can prove that variance is always a positive number, and so its square root is well defined in the positive numbers, and standard deviation is just a very small minor difference from variance. If you have a square root button on your calculator, let alone Wolfram Alpha, you can just think of the difference between standard deviation and variance as the difference between a positive number and its square root. Okay, so let's keep going with the example we've been consistently using and calculate the variance of the sum of the rolls of two fair dice. And we're going to apply epistemological best practices and copy the results of previous information processing rather than reprocessing information. So we have this table for the probability mass function of the random variable, and we can see I've just written out beneath, instead of the values, I need to think about the square of the values, because the formula I want to use is the one at the middle of the page on the very, very bottom, which is expectation of x squared minus mu squared. So e of x squared minus mu squared, that's the formula you want to stick in your head for practical computation of variance. And so what you need to do is you compute the probability mass function, and then instead of pairing up the values with the corresponding probabilities, you pair up the square of the values with the corresponding probabilities. So in the sum I have for variance, I have variance of x, and the first term is 4 times 1 over 36, because I have the probability mass function gives me 1 over 36 for the value of 2, and I'm going to pair up 4 with 1 over 36 because 4 is 2 squared, and I'm using the square to calculate e of x squared. So calculating e of x squared is something that cannot be done directly by information copying the result of mu, but luckily mu squared, you can just information copy the result of mu. So you see, after going through e of x squared and adding up all of these squares of values times probabilities, I've just subtracted 49 because in example 9.1 I calculated mu is 7 and I'm subtracting 7 squared. And this again, I have previously read from authoritative sources that the variance of sum of two rolls of fair die is 35 over 6, so I did not bother typing this into a computer. If you type this into a computer, it will tell you that it is 35 over 36, which is roughly 5.83. Okay. So, in terms of whether 5.83 is a high variance or a low variance, just wait and see for the rest of the course. Okay. So, I'll end the lecture here. Because of all the chaos that's been going on, homework 4, the next homework, is going to be assigned this coming Monday, and it's going to be due 2 weeks later on the day you return from spring break, March 22nd. So I guess theoretically you can do it during the week of classes prior to spring break, or you can procrastinate into it on spring break. Anyways, I'll stop there.